Hello dear students, Assalamu alaikum. I hope you will be fine. My name is Engineer Mir Masood Shah. I am lecturer in Department of Technology, Sarhad University of Science and Information Technology, Peshawar. As I am teaching you the subject fluid mechanics, today is your lecture number 4. In lecture number 4, we will continue the topic measurement of fluid pressure or measurement of pressure, in which we have in lecture number 3 we have already studied about piezometer and manometer, and also we have solved one example on how to calculate the pressure in the pipe. In lecture number 4 we will continue about that topic, and in lecture number 2 we will solve some example. So here example number 2.6, and the statement of the example is: a simple manometer is used to measure the pressure of oil having a specific gravity equal to 0.8 flowing in a pipeline. Its right limb is open to the atmosphere and the left limb is connected to the pipe. The center of the pipe is 90 mm below the level of mercury, having a specific gravity equal to 13.6 in the right limb. If difference of mercury levels in the two limbs is 150 mm, find the pressure of oil in the pipe. So in this example we have to find the pressure of oil in the pipe. A simple manometer is connected to the pipe in which oil is flowing, and the specific gravity of oil is given, which is 0.8 meter. Also, the right limb of the manometer is open to the atmosphere and the left limb is connected to the pipe as shown in figure. As you can see, the left limb is connected to the pipe while the right limb is open to the atmosphere. The center of the pipe is 90 mm below the level of mercury, as you can see in the figure, and the specific gravity of mercury is also given, which is 13.6. The difference of levels in the two limbs is also given, which is 150 mm, as you can see in the figure. We have to find the pressure in the pipe. So first of all, in solution we will write the given data. So S1 is equal to 0.8, which is the specific gravity of oil, and we denote specific gravity of oil by S1. Height of mercury above the center of the pipeline is equal to 90 mm. S2 is equal to 13.6. S2 is the specific gravity of mercury and it is equal to 13.6, already given in example. And H2 is equal to 150 mm and it is the height of the mercury column. So first of all we will calculate the height of oil, which is H1. So we will calculate from the geometry of the figure. From the geometry of the manometer we find that the height of oil column from the datum ZZ, H1 is equal to 150 minus 90 equal to 60 mm. So H1 is equal to 60 mm. The total height is given, which is 150 mm. We will minus this 90 and we will get this distance, which is equal to 60 mm. Let H is equal to gauge pressure in the pipeline in terms of water head. We know that pressure head in the left limb above ZZ is equal to H plus S1 H1. So if we cut this in the center, this is the left limb and this is the right limb. So pressure in the left limb above the datum is pressure in the pipe, which is H, and H is a pressure in the pipe in terms of head of water, while this pressure is equal to specific gravity into height H1. So specific gravity of this liquid is S1. So multiply S1 by H1, we will get the pressure in this area or this portion. So pressure in the left limb is above the datum line is equal to H plus S1 H1. S1 value is already given, which is 0.8, and H1 is also already calculated, which is 60 mm. So we will get in equation 1, which is equal to H plus 48 mm of water. Now the pressure head in the right limb above ZZ is equal to S2 H2. Pressure in the right limb is equal to specific gravity of this liquid multiplied by this height. So specific gravity of the liquid is S2 while this height is H2. values are given. S2 is equal to 13.6 already given in the given data, and S2 is already given, which is equal to 150 mm. So we will get the pressure in the right limb above the datum line ZZ is equal to 2040 mm of water. This is equation 2. Since the pressure in the both limbs above the ZZ means datum is equal, therefore equating equation 1 and 2, we have already studied that the pressure in the right limb and left limb are equal above the datum line. So equating equation 1 and 2, we will get H plus 48 is equal to 2040. Now move this 48 on the other side, we will get H is equal to 2040 minus 48, which is equal to 1992 millimeter. Divide this value by 1000, we will get H is equal to 1.992 meters of water, as 1 meter is equal to 1000 millimeter. Now we will find the gauge pressure of the oil in the pipe. So gauge pressure for or pressure of oil in the pipe, P is equal to omega oil into H. Now specific gravity of the oil is given, which is 0.8. So multiply this value by 9.8, which is the specific weight or unit weight of water at 4 degrees centigrade. We will get the unit weight of oil. H has been already calculated, which is 1.992. So we will get the pressure of oil in the pipe is equal to 15.62 kilopascal. And this is the answer of our example 2.6. Note, the value of H may also be obtained directly by the relation which has already been derived. H is equal to S2H2 minus S1H1. S2 is already given, H2 is already given, S1H1 are already given. So put the values, we will get this value, which is equal to 1992 millimeter equal to 1.992 meters. This is not millimeter, this is meter of water. So this is as same as the above. So through this way we will calculate the pressure in the pipe by using a simple manometer. Now we have example 2.7. The statement of example is a simple manometer containing mercury was used to find the negative pressure in the pipe containing water as shown in figure 2.7. The right limb of the manometer was open to the atmosphere. Find the negative pressure below the atmosphere in the pipe if the manometer readings are given in the figure. So a simple manometer is connected to the pipe as shown in figure 2.7. The left limb is connected to the pipe while the right limb is open to the atmosphere, and we have to find the negative pressure in the pipe. The readings are given in the figure. The reading of mercury in the left limb is 50 mm while the reading of water is 20 mm in the left limb. Given data, in solution we first of all write the given data. So in the given data, which is H2 is equal to 50 mm, which is the height of mercury. H1 is the height of water, which is 20 mm already given as shown in figure. Let S1 is equal to 1 because the specific gravity of water is 1 and the liquid flowing in the pipe is water. So specific gravity of water is equal to S1 equal to 1. And S2 is equal to 13.6 since the specific gravity of the specific gravity of mercury is 13.6. Let H is equal to gauge pressure in the pipe in terms of head of water. So H is the pressure in this pipe in terms of head of water. Now we will calculate the pressure in the left limb and right limb. So pressure in the left limb above the ZZ is equal to H plus S1 H1 plus S2 H2. Here you can see in figure, if we cut this through the center, this is the left limb, this is the right limb. So in the left limb we have pressure above the datum ZZ, pressure in the pipe, that is H, which is in terms of head of water, plus this pressure which is equal to S1 H1, and then this pressure which is equal to S2 H2. So putting the values of S1 H1 and S2 H2, we will get in equation 1, which is equal to S plus 700, that is equal to H plus 0.7 meter of water. Here it is written 7, but it is 0.7 because 1 meter is equal to 1000 millimeter, and when we divide 700 mm divided by 1000, we will get 0.7. So it is written mistakenly 7, it is 0.7 meters of water. Let this is equation 1. And pressure head in the right limb above ZZ is equal to 0. As you can see in the right limb, there is no head, so the pressure in the right limb is 0. Since the pressure in both the limbs above the ZZ datum is equal, therefore equating equation 1 and 2, as we have already studied that the pressure in the left limb and right limb are equal above the datum line. So equating equation 1 and 2, equation 1 is equal to H plus 0.7, again it is not 7, it is 0.7 equal to 0, or H is equal to minus 0.7, again it is not 7, it is 0.7, so it comes out to be H is equal to minus 0.7 meters of water. Now as we have to find the pressure, so we have formula for pressure P is equal to omega H. Since the liquid flowing in the pipe is water, so we will write the unit weight of water, which we already known is 9.81, and H is equal to, again it is not minus 7, it is minus 0.7. So we will get the pressure in the pipe by, you will get the pressure in the pipe by simply multiplying 9.81 multiplied by 0.7, minus 0.7. So we will get the pressure with a negative sign, which means the pressure in the pipe is negative. So through this way we can easily calculate the negative pressure in the pipe with the help of a simple manometer. If you want to remove this minus sign, you have to write a vacuum in the brackets, which means that the pressure in the pipe is negative. Next example is 2.8, and the statement of the problem is: the pressure of water flowing in a pipeline is measured by a manometer containing U-tubes as shown in figure 2.8. The measuring fluid is mercury in all the tubes and water is enclosed between the mercury columns. The last tube is open to the atmosphere. Find the pressure of oil in the pipeline. A simple manometer having multiple U-tubes as shown in figure is connected to the pipe, and we have to find the pressure in the pipe, and the measuring fluid is mercury, which is enclosed in the pipe. In the given data we have number of tubes is equal to 3. Since you can see in the figure there are 3 tubes used, 1, 2 and 3. So number of tubes is equal to 3. Height of mercury column in each column, height of mercury in each column is equal to 200 mm. So as you can see, this is the column or height of mercury above the datum ZZ. So mercury column height is equal to 200 mm. Here it is given. So 1, 2, 3. So the total height of mercury column H2 is equal to 3 multiplied by 200. Since there are 3 tubes, so 3 multiplied by 200 will give you the total height of mercury column, which is equal to 600 mm. Now total height of water H1 is equal to 300. Here it is 300 in the first tube, while in the second tube it is second and third tube it is 200. So 300 plus 2 tubes, in the 2 tubes it is 200. So 2 multiplied by 200 and plus this with 300, you will get the height of water column, which is equal to 700 mm. Let S1 is equal to 1 because the liquid flowing in the pipe is water, and S2 is equal to 13.6 because the heavy liquid is mercury and the specific gravity of mercury is 13.6. In the example, in the statement, there is written that we have to find the pressure of oil in the pipeline. It is not the oil, we have to find the pressure of water in the pipeline. mistakenly it is written oil, it is water. Clear? Then coming to the problem, let H is equal to gauge pressure in the pipe in terms of head of water. The pressure in the pipe, let it is denoted by H, which is in terms of head of water, which is the gauge pressure in terms of head of water. Now we know that pressure head due to water above ZZ is equal to H plus S1 H1. So pressure H1 is the pressure in the pipe, while S1 H1 is the pressure of water in the tubes. So S1 is the specific gravity of liquid, which is water, and which is equal to 1, while H1 is already calculated, which is the total height of water column, and it is equal to 700. So we will get an equation 1, which is equal to H plus 0.7 meters of water. Then we have to find the pressure due to mercury above the ZZ, and it is equal to S2H2. Since the S2 is equal to 13.6, because the heavy liquid in the tubes is mercury, and H2 is already calculated, which is equal to 600, which is the height of the mercury columns. So we will get an equation 2, which is equal to 8.16 meters of water. Since the pressure head due to water and mercury are equal, therefore equating equation 1 and 2, since the pressure in the tubes or the pressure of water and the mercury column above the datum line are equal, so equating equation 1 and 2, equation 1 we have H plus 0.7 equal to equation 2 8.16. Move this 0.7 on the other side, we will get the value of H, which is equal to 7.46 meters of water. Now we have to calculate the gauge pressure or pressure of water in the pipeline. Again, it is not oil, it is water in the pipeline. We have equation P is equal to omega H. Since the liquid flowing in the pipe is water, so the value of omega is 9.81. H is already been calculated 7.46, so multiply 9.81 with 7.46, you will get the pressure in the pipe, which is equal to 73.2 kilonewton per square meter, which is equal to 73.2 kilopascal. And this is the answer of our example 2.8. The next topic we have differential manometer. It is a device used for measuring the difference of pressures between 2 points in a pipe or in two different pipes. A differential manometer in its simplest form consists of U tubes containing a heavy liquid whose two ends are connected to the points whose difference of pressure is required to be found out. So a differential manometer is a device which is used for finding difference of pressures between the 2 points or between the two pipes. In its simplest form, the differential manometer consists of a U tube in which a U tube containing a heavy liquid, and the two ends are connected with the pipe or with the two different pipes or within the same pipe at two different points. So with the help of differential manometer, we can easily find the difference of pressure between the two pipes in this between the 2 points in the same pipe or in the two different pipes. To find the pressure in the pipe through differential manometer, now consider a differential manometer whose two ends are connected with two different points A and B as shown in figure 2.17a and B. Here a differential manometer is connected with 2 points A and B. The differential manometer consists of a U tube having mercury in the U tube as shown in figure A and B. Let us assume that the pressure at point A is more than the pressure at point B. A little consideration will show that the greater pressure at A will force the heavy liquid in the U tube to move downward. This downward movement of the heavy liquid in the left limb will cause a corresponding rise of the heavy liquid in the right limb as shown in figure 2.17a. Let us assume that the pressure at this point A is greater than this point B. So as a result, this pressure exerts pressure on the heavy liquid and tends to move this heavy liquid downward. As a result, the heavy liquid moves upward in the right limb. Let us take the horizontal surface ZZ at which the heavy liquid and right limb meet in the left limb as the datum line. Let this be the, at this point they balance each other, so let this be the common point or datum line, and it is denoted by ZZ. Let H is equal to difference of the levels of the heavy liquids in the right limb and left limb, also known as the reading of the differential manometer. HA is equal to pressure head in the pipe at A, while HB is equal to pressure head in pipe B. S1 is equal to specific gravity of the light liquid in the pipes, and S2 is equal to specific gravity of the heavy liquid. Now we know that pressure head in the left limb above ZZ is equal to HA plus S1 capital H plus H. Here you can see, if we cut this in the middle, this is the left limb, this is the right limb. So pressure in the left limb is equal to HA, which is pressure at point A in terms of head of water, plus this readings or this height of this height, which is H plus small h, and the liquid in this column is S1. So the pressure in this column from this point up to this point is S1 multiplied by H plus H. So this is the pressure in the left limb. Simplify this, you will get HA plus S1 capital H plus S1 small h meters of water. Let this is equation 1. Now pressure head in the right limb above ZZ is equal to HB plus S1 capital H plus S2 small h meters of water. Now pressure in the right limb is equal to pressure HB, which is pressure in the pressure head at point B in terms of head of water, plus S1, the specific gravity of this liquid is S1 multiplied by H, will give you the pressure up to this point, while the next high head we have is H, so and the specific gravity of this liquid is S2, so S2 multiplied by this small h will give you the pressure head of this column. So the total pressure in the right limb is equal to HB plus S1 capital H plus S2 small h, and let this is equation number 2. Since the pressure head in both the limbs above ZZ means datum are equal, therefore equating the equation 1 and 2, as we already studied that the pressure in the left limb and right limb above the datum line are equal, so equating equation 1 and 2, we get HA plus S1 capital H plus S1 small h is equal to HB plus S1 capital H plus S2 small h. This S1H and this S1H is common on both sides, so this will cancel out, and we will get HA minus HB means the difference of pressure between the 2 points is equal to S2H minus S1H, or this is equal to taking H common, we will get H into S2 minus S1. So this will give you the pressure head or difference of pressure between the 2 points, which is A and B. Sometimes the 2 pipes or the 2 points whose difference of pressure is required to be found out are not at the same level, and at the same time the liquids flowing in the 2 pipes are different. In such a case, the same principle is applied to obtain the difference of pressure in the heads. The above equation is derived for the condition that the liquid flowing in the pipe is same and the points are at the same level. In the second case, we have 2 different points whose levels are also different, and also the liquid flowing in these 2 points is different. So the calculation of pressure is the same, or the principle is the same as in the case of the above, or as in the above case. For this, now consider a differential manometer whose 2 ends are connected to 2 different pipes A and B and containing different liquids at different level as shown in figure 2.17b. Here it is the figure 2.17b. 2 pipes A and B at different levels are connected to a differential manometer as shown in figure. In pipe A, the liquid is changed or different from the liquid in the pipe B. Let us assume that the pressure at point A is more than the pressure at point B. A later consideration will show that the greater pressure at A will force the heavy liquid to move downward. This downward movement of the liquid in the left limb will cause a corresponding rise of the heavy liquid in the right limb as shown in figure 2.17b. Let us assume that the pressure in pipe A is more than the pressure in pipe B. As a result, the pressure in pipe A exerts pressure on the heavy liquid in the U-tube to move downward. As a result, the liquid will rise in the heavy liquid will rise in the right limb. The horizontal surface at which the heavy and light liquid meet in the left limb is taken as datum line. In this case, let ZZ be the datum line as shown in figure 2.17b. So let this ZZ be the common point or datum line, and it is denoted by ZZ. Let H1 is equal to height of liquid in the left limb above the datum line in mm, and H2 is equal to difference of levels of the heavy liquid in the right limb and left limb as shown in figure, also known as reading of the differential manometer in mm, and H3 is equal to height of the liquid in the right limb above the datum line in the mm. This is H1, height of the liquid which is flowing in pipe A, while H3 is equal to height of the liquid which is flowing in pipe B, and H3 is the height of the mercury column. HA is equal to pressure head in pipe A, while HB is equal to pressure head in pipe B. HA is the pressure in terms of head of water at pipe A in pipe A, while HB is equal to pressure in terms of head of water in pipe B. S1 is equal to specific gravity of the liquid in the left pipe, while S2 is equal to specific gravity of the heavy liquid, and S3 is equal to specific gravity of the liquid in the right pipe. The specific gravity of the liquid flowing in pipe A is denoted by S1, while the specific gravity of the liquid flowing in pipe B is denoted by S3, while the specific gravity of mercury is denoted by S2. Now we know that pressure in the left limb above the datum ZZ is equal to HA plus S1 H1 meters of water. Let this is equation 1. Here, as you can see in the figure, if we cut this in the middle, this is the left limb, this is the right limb. So pressure in the left limb is equal to pressure in the pipe plus pressure in this column. So pressure in the pipe is equal to HA, which is pressure in terms of head of water, plus this liquid specific gravity is S1, multiply S1 by H1, we will get the pressure of this column. So S1 multiplied by H1 will give you the pressure of this column. So total pressure in the left limb is equal to HA plus S1 H1. Similarly, and pressure in the right limb above the datum ZZ is equal to S2 H2 plus S3 H3 plus HB meters of water. Let this is equation B. Now pressure in the right limb is equal to pressure in the pipe, which is denoted by HB, which is in terms of head of water, plus pressure of this column, which is denoted by H3. Multiply this by H3, the specific gravity of the liquid in this column, you will get the pressure of this column, and multiply H2 by S2, we will get the pressure of this column. So total pressure in the right limb is equal to HB plus H3 S3 plus S2 H2. Since the pressure in both the limbs above ZZ datum is equal, therefore equating these two equations these two pressures, we already studied that the pressure above the datum line are equal in both the limbs. So equating equation 1 and 2, we get HA plus S1 H1 plus S2 H2 plus S3 H3 plus HB. From the above equation, the value of HA, HB or their difference may be found out. This is the final equation. You can find the value of HA, or if you want to find the value of HB, also you can find the difference between these 2 points HA and HB. So this is the final equation of the differential manometer if the liquids in the two pipes are different and the pipes are at different level. We have example 2.10 and the statement is a differential manometer connected at 2 points A and B at the same level in the pipe containing an oil of specific gravity 0.8 shows a difference in mercury level as 100 mm. Determine the difference in pressure at the 2 points. So in the figure we have a differential manometer which is connected to 2 points A and B, and the level of these 2 points is same, and the liquid flowing in these 2 points is also same. The liquid in these at these 2 points is oil whose specific gravity is given, which is 0.8. Also the level of mercury is given, which is equal to 100 mm, and we have to find the difference of pressure between these 2 points. First of all, we will write the given data. In given data we have S1 is equal to 0.8, which is the specific gravity of oil flowing in the pipe. H1 is equal to 100 mm, which is the height of mercury column, and S2 is equal to 13.6, which is the specific gravity of mercury. Now we know that pressure in the left limb above ZZ is equal to HA plus S1 into H plus capital H plus 100. Here if we cut this in the middle, this is the left limb, this is the right limb. So pressure in the left limb is equal to HA, which is pressure in the pipe which is pressure at point A in terms of head of water, plus pressure in this column. So this column height is equal to this capital H plus 100. And multiplying this height by S1 we will get the pressure in this column. So pressure in the left limb is equal to HA plus S1 into capital H plus 100 mm of water. We will simplify this, we will get HA plus S1 capital H plus 100 S1 mm of water. Let this is equation 1. Now pressure in the right limb above the datum ZZ is equal to pressure in the pipe, which is denoted by HB in terms of head of water, plus height of this column, which is capital S1, which is capital H, and multiply this capital H by S1 we will get the pressure of this column, and then we have pressure of this column. So multiply this by specific gravity of this liquid, which is S2 multiplied by 100. So we will get the pressure in the right limb equal to HB plus S1 capital H plus S2 into 100 of mm of water. Now since the pressure head in both the limbs above the datum ZZ are equal, therefore equating equation 1 and 2. Let this be equation 2. So equating equation 1 and 2, because the pressure above the datum line are equal. So equating equation 1 and 2 we get HA plus S1 capital H plus 100 S1 equal to HB plus S1 H capital H plus 100 S2. This S1 capital H will cancel out with this S1 capital H because they are common on both the sides. Move this HB on the other side, we will get HA minus HB is equal to 100 S2 minus 100 S1. Take out 100 common, we will get equal to 100 S2 minus S1. Put the value of S2 and S1. S2 is equal to 13.6 because it is mercury, and S1 is equal to 0.8 already given, the specific gravity of oil. So we will get the value of 12.8 from this. So multiply this by 100, we will get the difference of pressure head HA minus HB is equal to 1280 mm. Divide this by 1000, so we will get this value in meter, which is equal to 1.28 meters of water. So this is the difference of head between these 2 points A and B. Now to find the difference of pressure between the 2 points, we have formula P is equal to omega H. So since H is the difference between the 2 points, so put the value of HA minus HB. Also the unit weight of the liquid is equal to 0.8, which is the specific gravity of oil. Multiply the specific gravity of oil by 9.81, which is the specific gravity of water, the specific weight of water. So we will get the unit weight of oil. Multiply the unit weight of oil by the difference of pressure, we will get the difference of pressure between the 2 points, which is equal to 10.04 kilopascal. And this is the answer of our example 2.10. Now we have topic Bourdon's tube pressure gauge. The pressure above or below the atmospheric pressure may be easily measured with the help of a Bourdon's tube pressure gauge. A Bourdon's tube pressure gauge in its simplest form consists of an elliptical tube ABC bent in an arc of a circle as shown in figure 2.23. This bent up tube is called Bourdon's tube. The Bourdon's tube is used to measure the gauge pressure. The Bourdon's tube consists of an elliptical tube ABC as shown in figure, which is bent into an arc of circle as shown in figure. This bent up tube is called Bourdon's tube. When the tube gauge is connected to the fluid whose pressure is to be found out at C, the fluid under pressure flows into the tube. The Bourdon's tube, as a result of the increased pressure, tends to straighten itself. Since the tube is encased in a circular cover, therefore it tends to become circular instead of straight. With the help of a simple pinion and sector arrangement, the elastic deformation of the Bourdon's tube rotates the pointer. This pointer moves over a calibrated scale which directly gives the pressure as shown in figure. So to find the pressure with the help of Bourdon's tube pressure gauge, the tube is connected at point C and the wall is open. As you open the wall, the pressure moves in the tube with high pressure. As a result, this tube tends to straighten itself, but as it is enclosed in a circular cover, it rotates through a calibrated scale and gives the pressure directly. And this is the end of our today's lecture.